Hi, future scientists. I am Atom. Join me in this journey, and together let us unravel the physics of inverse square law. Scenario 1. Light. Isaac is on a night hike. It is pitch black, and the only light source is his flashlight. Ever wondered why objects closer to the light source are brighter and objects far away appear dim? Why doesn't the light stay uniform? Well, it's time to shed some light on the inverse square law. The inverse square law states that the intensity of a physical quantity diminishes with the square of the distance from the source. Let us understand this phenomenon with the help of some geometry. Imagine we have a light bulb as our point light source, which has a power P watts. Let us say the intensity of the light is I units at the source. Now we add a sphere of radius r around the light source. The surface area of a sphere is 4 pi r square, where r is the radius of the sphere. The intensity of the light source is spread over an area of 4 pi r square. Or we can say that the intensity I1 equals P divided by 4 pi r square. So the unit for intensity of light is watts divided by square meter. Now we add a second sphere of radius 2r. The surface area of this sphere is 4 pi times 2r squared. The intensity of the light source is spread over a larger area of 16 pi r square. Or we can say that the intensity I2 equals P divided by 4 pi times 2r the whole squared, which equals P divided by 16 pi r square. Now we add a third sphere of radius 3r. The surface area of a sphere in this case is 4 pi times 3r the whole square. The intensity of the light source is spread over a larger area of 36 pi r square. Or we can say that the intensity I3 equals P divided by 4 pi times 3r the whole square, which equals P divided by 36 pi r square. Now let us study the pattern between the light intensity and the radius of the sphere. At a distance r from the point source, the light intensity is I1, which equals P divided by 4 pi r square. At a distance 2 times r, the light intensity is I2, which equals P divided by 16 pi r square. Or we can say I2 equals I1 times 1 over 4. It becomes 1/4. At a distance 3 times r, the light intensity is I3, which equals P divided by 36 pi r square. Or we can say I3 equals I1 times 1 over 9. So we can say the light intensity is inversely proportional to the square of the distance from the light source. I is proportional to 1 over r square, and that is inverse square law. Scenario 2. Gravity. Here, let us explore a force that keeps us grounded: gravity. According to the inverse square law, the force of gravity between two objects is inversely proportional to the square of the distance between their centers. Mathematically, the gravity force F is proportional to 1 over d square, where d is the distance between the centers of the two objects. This law explains why, as you move away from a massive object like the Earth, the gravitational pull weakens. Scenario 3. Electricity. When you use a Van de Graaff generator, your hair stands up as you touch the dome. But as you move away, the electric field's grip loosens. The strength of the electric field weakens as distance increases. F proportional to 1 over d square. Here, F is the electric force and d is the distance between the centers of the two charged bodies. Think about your Wi-Fi router in your home. The signal strength diminishes as you move further away, right? That is the inverse square law, making sure you stay connected within a certain range. Scenario 4. Radiation. If you use a Geiger counter near a radioactive source, the clicks are louder. As you retreat, the clicks become fainter. That is inverse square law at work. Be it X-rays, gamma rays, or any type of radiation, the further you are from the source, the weaker the impact. Doctors carefully control the distance between the patient and the X-ray source to ensure accurate and safe imaging. The principle of inverse square law is considered in the design and operation of CT scans to ensure accurate and safe imaging. Scenario 5. Sound. Move towards a sound source, like a speaker, and the sound intensity increases in accordance with the inverse square law. Now, keep moving away from the speaker till you find a quiet spot. The beats become distant, faint, and hard to hear. It is like the inverse square law is orchestrating a dynamic concert where the distance is dictating the melody. In an auditorium, engineers mitigate the effects of the inverse square law on sound intensity through strategic acoustic design. This involves carefully placing sound reflecting surfaces and using specialized panels to ensure that sound waves reflect off surfaces, maintaining their intensity. Also, advanced sound reinforcement systems with strategically positioned speakers and amplifiers help distribute the sound evenly throughout the space. This counteracts the reduction in the strength of the sound waves predicted by inverse square law and ensures an optimal acoustic experience for the audience. Now, for some challenge questions. Question 1. Ion uses a flashlight that has an intensity of 100 units. If she moves twice as far away from the flashlight, how much light intensity will she experience? If Ion moves twice as far, the light intensity will be equal to 100 units times 1/4, which equals 25 units. Suppose you have two masses, each weighing 100 kilograms. They're initially 2 meters apart. If you double the distance between them, what happens to the gravitational force? If the masses move 2 times away from each other, the gravitational force will be equal to 1/4 times its original strength. Question 3. Ion has a charged balloon, creating an electric field. And if she moves 3 times further away from it, how does the strength of the electric field change? Since Ion moves 3 times further away, the strength of the electric field will be equal to 1/9 the original strength. Question 4. Isaac is in a laboratory with a radioactive source emitting a certain amount of radiation. If he moves 4 times further away from the source, what happens to the intensity of the radiation he is exposed to? When Isaac moves 4 times further away, the intensity of the radiation will be equal to 1/16 its original intensity. Question 5. Isaac and Ion are at a concert, and the sound system is pumping out 90 decibels of sound. If they decide to enjoy the concert from a spot twice as far from the speakers, how loud will the music be at their new location? If they move twice as far, the sound intensity at their new location will be equal to 90 decibels times 1/4, which equals 22.5 decibels. Question 6. Ion is standing 100 meters from a speaker emitting music. She moves toward the speaker until she is 10 meters from it. What happens to the intensity of the sound of the music that Ion experiences? Ion moves 10 times closer to the source, so the sound intensity gets 10 square or 100 times louder. Question 7. Isaac experiences the intensity of a sound wave at 2 times 10 to the -3 watts per square meter when he is 2 meters from the speaker. What is the intensity of the sound wave when he is 5 meters away from the speaker? I1 is proportional to 1 divided by R1 square, where I1 is the initial intensity and R1 is the initial distance. The same way, I2 is proportional to 1 divided by R2 square, where I2 is the final intensity and R2 is the final distance. So since we have I1 proportional to 1 over R1 squared and I2 proportional to 1 over R2 square, we can combine these two and write it as I1 divided by I2 equals R2 square divided by R1 square. Now, the given data says I1 equals 2 times 10 to the negative 3 watts per square meter. R1 is 2 meters and R2 is 5 meters. So we can write I2 equals I1 times R1 square divided by R2 square. Now plugging in the values of I1, R1 and R2, we get I2 equals 3.2 times 10 to the negative 4 watts per square meter. From the behavior of light to the forces of gravity, electricity, intensity of sound and radiation, we have unveiled the physics behind the inverse square law. If you enjoyed this adventure through physics, please don't forget to like, share, and subscribe for more intriguing insights into the science around us. Share your thoughts on what other physics and chemistry concepts captivate your interest in the comment box. Happy learning! Thank you.